Welcome back to this video. Today I'm going to show you two examples of how to apply Green's theorem. We're going to see one example that illustrates how to compute a volume integral using a line integral. And we'll see another example that illustrates the other way around, computing a line integral using a volume integral. So with Green's theorem, you're basically free to use whatever way is easier for you. Before we start with the examples, let's quickly remind you how Green's theorem looks like. So the formula for Green's theorem is the integral along the boundary of a domain B, VDS, for a vector field V, that is equal to the integral over B, the volume integral, over the function dv2 dx1 minus dv1 dx2 dx1 x2. So on the right we have a volume integral, on the left we have a line integral. So for our first example we are going to consider a vector field in the plane. Remember, for Green's theorem we are always in the plane. It just works in R2, no higher dimensions here. We're just going to consider the rotation field that we know already. It's defined as minus x2 and x1. For B, we are going to take the following domain. We're going to look at all points x1, x2 in R2, such that x1 squared plus x2 squared is less or equal to 1, and x2 is greater or equal to 0. So what we have here is basically a disk. So this is a description of the unit disk with a radius 1. And this here cuts off one half of the disk, so we only consider points where x2 is non-negative. So let's go for a quick sketch of this domain. So here's x1, here's x2. Then the domain basically looks like the half disk. Okay, so this is B, that half disk. Here's minus 1. Here's 1, and here's 1 as well. So first thing we need to do if we want to use Green's theorem is we need to parameterize the border of B. That border is given like this. So the first part is we need to find a parameterization of that border. And you can basically see that this border consists of two pieces. We have that straight line here, this part here, and we have a half circle here. So we'll consider those separately. And we start with first piece, we'll call that gamma 1, and we call that piece here gamma 2. There will be one closed curve, but consisting of two parts. So we are going to come up with a closed curve gamma consisting of differentiable parts gamma 1 and gamma 2. And now we need to find suitable parameterizations. For gamma 1, that's easy. So we just use gamma 1, we just need to set the second coordinate, the x2 coordinate, to 0. And we need to vary the x1 coordinate between minus 1 and 1. So the easiest way to parameterize this is probably to take the interval from minus 1 to 1, map that to R2. And our mapping is gamma 1 of t is just t and 0. Then this first coordinate here, this varies between -1 and 1. And the second one is always 0, so we'll get exactly this curve. The second curve, that's the half circle. So we do know the description for the circle. You remember that can be parameterized as cosine t, sine of t. And the parameter for moving around the whole circle, that t will vary from 0 to 2 pi. Now, the starting point is this one here, cosine of 0, sine of 0. And then that parameterization moves in that direction, and we need to stop here. And that is exactly where the parameter t reaches pi. So we need to restrict our parameter space here from 0 to pi. So these are our curves. Let's make sure we got the direction right. Otherwise we need to reverse that possibly. So here for the first curve, we start at t equals -1 and move towards higher values. So that curve starts here and then moves in this direction. And to the left of that direction is b. So that's fine. For that circle part here, we start here and move this way. That's our current movement direction. So that would be parameterized like this. That is the direction of traversal. And that means left of the traversal direction is here. So that also points towards b. Okay, so b actually is to the left of those curves of both gamma 1 and gamma 2 with respect to their direction of traversal. Had that not been the case, you would have had to flip one or both of these curves appropriately. Okay, so that means we have the two curves. We can now compute this volume integral here on the left, this integral here, by computing the integral over the vector field along the boundary of B. So that means we can now apply Green's theorem. So in this case, with the vector field that we have, let's compute that. This is the vector field minus x1 and x2, and we integrate the volume integral over this expression here. So let's compute that first. So dv2 dx1 minus dv1 dx2 of x. Well, what is that? Our vector field here is this. So dv2 dx1, this means we have to differentiate this with respect to x1, that's 1. And this is v1, and we have to differentiate that with respect to x2, that's a minus 1. You will possibly remember we already did that when we've talked about divergence and rotation. So we get a 1 here, and we get minus 1, so that's a 2. Okay, so what does that mean? We will compute the integral over b of dv2 dx1 minus dv1 dx2 of x dx1 x2. That is exactly the integral over b of 2 dx1 x2. And this integral is basically the volume of b, but with a factor of 2. So this is 2 times the volume of b. So we find a way to compute the volume of b here. And that should make it easy to verify the results, because of course you know what the volume of the half disk is, hopefully. Okay, so we're going to use that. That means 2 volume of b is, by Green's theorem, equal to the integral of VDS along the boundary of b. And that is equal to the integral over gamma 1 VDS plus the integral over gamma 2 VDS. And you know how to evaluate these integrals. So this is, for the first curve, the integral from -1 to 1 over v of gamma 1 of t, scalar product with gamma 1 dot of t dt. And the second one, we integrate from 0 to pi minus, the integral of v of gamma 2 of t with gamma 2 dot of t dt. So what do we get here? Let's see. V of gamma 1, remember v, let's write that somewhere, v was the vector field minus x2, x1. Gamma 1 is the curve t0. So if we insert that here, we get t for the first coordinate, 0 for the second. So v of t0, that is 0 or minus 0 and t. And then we need gamma 1 dot. Again, gamma 1 is t0. So gamma 1 dot is just 1, 0. Okay, so here we get the vector 1, 0. And we want the scalar product of that dt plus integral from 0 to pi. Gamma 2, remember that was cosine of t, sine of t. So if we substitute that into the vector field v, we flip the order of the coordinates, plus the first one gets a minus sign. So we have minus sine of t, cosine of t. And then we have gamma dot. Now, the derivative of the cosine of t is the negative sign. So there's minus sine of t. And the derivative of the sine is the cosine of t. So this is how that integral looks like. And now we're down to just simple one-dimensional integration, basically. So that first scalar product is 0. Not much to integrate there. And the second one, that yields sine squared of t plus cosine squared of t dt. So that is simply the integral from 0 to pi of 1 dt. And it doesn't get a lot easier than that, as you know. So what we get here is, as a result, t, and the boundaries are 0 and pi. So substituting these, the result is pi. So pi is twice that volume here. And that means the actual volume of B, the area of that half disk, is pi over 2. And if you remember, hopefully you remember, the area of a disk with radius r is r squared pi. Radius is 1 in this case, so here we get pi, and that means the half disk has an area of pi over 2. So from what you know about geometry, this is easily verified. Okay, so this is the first example for Green's theorem. And now we'll see another one, second example. It demonstrates you how we could apply that in the other way. Again, we want a vector field. V of x1, x2 is now, let's say, minus x2 to the third and x1, x2 squared, to make these integrals a little more interesting. And B, let's say we want B to be the parallelotope with vertices 0, 0, 1, 0, 1, 1, and 2, 1. Again, it's probably a good idea to make a quick sketch here. So our parallelotope looks like this. We have 0, 0. We have 1, 0. We have 1, 1. So moving here. And then we have 2, 1. This is here, right? So this here is our set B. And again, there's 1, 1 here and 2, 1 here. And you can see the set B can easily be described so this consists of all the x1, x2 in R2 with, well, x2 varies between 0 and 1. So that's the easy coordinate, so to say. 0 is less or equal to x2 is less or equal to 1. And then x1 depends on x2 in a very simple way. So here's the x1 coordinates. This is the line x1 equals x2. And this is the line x1 equals x2 plus 1. And x1 just varies between those two lines here. So we get x2 is less or equal to x1 is less or equal to x2 plus 1. Right, so this line here, that is x2 equals x1. And that is the line x2 equals x1 minus 1, or x1 equals x2 plus 1. Okay, so B can be described in this way, and that means we have a normal domain here. And integration over a normal domain is something that we know how to do. So if you want to compute the line integral over our vector field along the boundary of B, then we can do that by evaluating a more or less simple volume integral. The line integral along this boundary here would be more complicated, probably because we have to evaluate 4 different integrals. We need those 4 pieces here because there's points of non-differentiability at the vertices. The direction of traversal here needs to be this, of course, because, as you know, We have to make sure that B is to the left of our traversal direction. Okay, and this orange part here, that is the boundary of B, and that is piecewise differentiable, as you can easily see. So if you want to compute the line integral along the boundary of B of VDS, then we can do this by computing the integral over B, the volume integral over B, of the following expression: dv2 dx1 minus dv1 dx2 dx1 x2. And as I said, B is a normal domain. We do know how to integrate over normal domains, so this should not be too complicated. We do need to compute this expression here though. So v2 is this here, and we need to differentiate v2 with respect to x1. So that's just x2 squared. And then we need to compute this derivative here, dv1 with respect to dx2. v1 is minus x2 to the third. So differentiating that with respect to x2, we get minus 3x2 squared. And we integrate that dx1 x2. Okay, so that is simply the integral over minus 2 x2 squared dx1 x2. We know the description of B already, and this is a continuous function, so nothing can go wrong here if we apply Fubini's theorem. So that means we can just use integration over normal domains as we used to. Let's take out the minus 2 to make things even more easy. The outer integral needs to go over x2. x2 is from 0 to 1. The inner integral is then x1. And let's look at the description of B here. x1 has boundaries x2 as a lower bound and x2 plus 1 as an upper bound. So that's x2, x2 plus 1. And we integrate x2 squared dx1 dx2. So let's now we have minus 2. We'll evaluate the inner integral first. So let's copy the outer integral here. We need to integrate with respect to x1. There is no x1 yet in that expression. So we have x2 squared times x1. And our boundaries here are x2 and x2 plus 1 dx2. So what we get is minus 2 times this integral over x2 from 0 to 1 of x2 squared times upper bound x2 plus 1 minus lower bound, that's x2 dx2. So this becomes extremely simple. We have minus 2, the integral of x2 from 0 to 1 x2 squared, and this expression here just becomes 1. So we can finally integrate that x2 expression, and we have minus 2 times the integral over x2 to the third over 3 x2 from 0 to 1. So what we get is minus 2. Upper bound is 1, so we get 1/3. Lower bound is 0, so that's minus 0. And that means, finally, we have that integral here that is minus 2 over 3 as our final result. So we computed that integral over the boundary of our domain, of our B, using just the volume integral. And that means we didn't have to compute 4 single integrals of that boundary, because we would have needed 4 different curves due to these vertices here. This way you could just evaluate one integral as a volume integral, and that made things a little easier here, hopefully. So those are scenarios where Green's theorem can be applied, and you'll see more of those in the exercise sheets. So that concludes these examples on Green's theorem. Thank you for your attention, and goodbye.